My name is Dang Song. I'm a professor in computer science at UC Berkeley and also a co-director of a campus-wide center called Berkeley Center for Responsible Decentralized Intelligence. So today, I'm particularly excited to give the keynote here because ICLR actually holds a special place in my heart. I first went to the ICLR in Puerto Rico in 2016. Back then, there were only a few hundred attendees. That was the good old days, whereas today there are apparently 12,000 attendees. And also, my first paper at ICLR was 2017 in Toulon, and that also won the Best Paper Award at ICLR, making neural programming architectures generalized by recursion. One of the earliest papers in using deep learning for program synthesis and to achieve generalization. And also, I actually had the honor to be a program co-chair for ICLR 2020. And we were really excited to hold it in Africa to be the first top machine learning conference ever taking place in Africa. Unfortunately, due to COVID, we had to change it to virtual. And I'm really excited to be here this time in Singapore. And also thanks for the Outstanding Paper Honorable Mention Award for one of our papers as well. So with that, let me start my talk. So first, we are all really excited about the fast advancements in frontier AI. And also the year 2025 has been named the Year of Agents by many. However, at the same time, also there's a broad spectrum of AI risks. As listed here, from the recently released International AI Safety Report, led by Joshua Benjo, and in collaboration with 100 leading AI researchers from 30 countries, and I'm also part of this report. And also I want to stress that as we deploy AI, it's particularly important to consider AI in the presence of attackers for a number of reasons. History has shown that attackers always follow the footsteps of new technology development, or sometimes even lead it. And also this time, the stake is even higher with AI. As AI controls more advanced systems, attackers will have higher and higher incentives to compromise them. And also as AI becomes more and more capable, consequences of misuse by attackers will also become more and more severe. And hence, it's really important to consider the adversarial setting when we develop safe and responsible AI. And I also wanted to briefly mention AI safety versus AI security. These two are interrelated. AI safety aims at preventing harm that a system might inflict upon the external environment, whereas AI safety aims to protect the system itself against harm and exploitation from malicious external actors. And AI safety needs to consider adversarial setting. For example, alignment mechanisms need to be resilient and secure against attacks. And hence, AI safety also needs AI security. So overall, our goal is to advance safe and secure AI innovation to ensure its potential benefits are responsibly realized and widely shared. But AI safety and security is a huge topic. Due to interest of time, I won't be able to cover everything. So here, in my talk, I will mainly cover two sets of topics. First, looking at challenges, how to ensure trustworthiness of AI and AI alignments when we deploy AI. And the second set of challenges for mitigating misuse of AI. And at the end, I will also talk about our recent proposal on a path for science and evidence-based AI policy. First, when we look at how to ensure trustworthiness of AI and AI alignments when we deploy AI in practice. Again, there is a broad spectrum of different topics and aspects in this domain. Again, given interest of time, I won't be able to cover everything. So in this talk, instead, I will select a few topics based on my own journey in this area and share the lessons, some of the lessons that I have learned from my own journey. And also to start, I wanted to share a little bit, just some anecdote of my journey actually started in a little bit of an unusual way. Up until I got tenure, my main research area has been in computer security and privacy. Although I have been using machine learning for security applications. So in 2009, the summer, I got tenure at Berkeley. And my present to myself for tenure was to go to a summer school in computational neuroscience for 1 month at the Woods Hole outside of Boston. So I've always wanted to build intelligent machines. So this was a great present to myself for getting tenure. And that also started my journey with deep learning. So people say that the point of getting tenure is that you are free. You are free to work on whatever you want. So I was glad that I was able to take advantage of that. So I guess this is the first lesson for junior faculty, or just in general for faculty, that you should take advantage once you get tenure to do whatever, to work on whatever you want. Okay, so here I will share a couple topics in this area and sharing some lessons learned from my journey. So the first one is privacy. As we all know, neural networks has huge capacity. And one question is, do neural networks actually remember training data? And if yes, can attackers extract secrets from the training data from just simply querying the learned models without even knowing the details of the models, such as the architecture of the models and the parameters? So my group, with our collaborators from Google, was the first to set out to investigate this question. So this was early on language models. From our early study, here's an example of a case study where we trained a language model on a public email dataset called the Enron email dataset, which naturally contained users' credit card numbers and social security numbers. And our work showed that by devising new attacks, attackers can automatically extract some of these secrets, users' credit card and social security numbers that were embedded in the original training data from just simply querying the trained models. And hence, was for the first time illustrating that even as we train machine learning models, it's important to protect users' data privacy as these models can remember training data, and attackers can leverage and exploit this. We also developed a new measure called exposure to measure a degree of memorization, and this measure has been used in Google's products such as Smart Compose. So fast forward, as the models continue to improve and become larger, we continue to investigate in this domain. So our follow-on work also showed that as we studied back then the largest language model, GPT-2, and illustrating that these models also remember training data, and attackers can actually extract even more actually sensitive data from the training data from querying these models. So here's an example of our device attack, the prefix-based training data extraction attack, where you can provide various prefix, and the model will return from the model output. Oftentimes, some of these attacks, the model will output memorized training data. And here's an example of memorized training data containing personally identifiable information. So moving forward in our recent work, Decoding Trust, the first comprehensive evaluation framework for trustworthiness of large language models. So this work also, with collaborators, this work also won the Best Paper Award at NeurIPS, and also the Best Scientific Cybersecurity Paper Awards of year 2024, given by the NSA. And each year, NSA gives out one paper award, and last year was for this one. So in this work, we also set out to develop a comprehensive evaluation framework to evaluate many different perspectives of trustworthiness and one of them is on privacy and memorization. And in this work, by developing various different prompting techniques, we also illustrated that as for these foundation models, again, they memorize training data, and with these various prompting techniques, attackers can get sensitive information from the training data, again, such as personally identifiable information. And by other researchers, there's also interesting phenomena that, for example, here, when you give this prompt to GPT, the GPT starts to output following the instructions. For example, here, starts to output the point many times. And at some point, the model actually gets into a weird state, starts to output some text here. And actually, there's later on, there's confirmation that the output text actually is from a user's email signature, illustrating that, again, this is an example of actually real-world occurrences and implication of memorization, where these large language models memorize training data, and they can get into these weird states that they start to just spew out training data. And also, in our recent work, we also expanded the scope to, and also developed a comprehensive assessment framework to look at data privacy issues throughout the different stages of large language model development, including pre-training, fine-tuning, and in-context learning, and so on, and look at many different types of attacks beyond just data extraction attacks, and so on, and also different defenses. And the work won the Best Paper Award finalist at a top conference. So in this work, using this comprehensive assessment framework, we were able to systematically explore many different questions related to data privacy in large language models. Here's just one example of insights from our study. In particular, we wanted to study the relationship of factors that impact privacy leakage. For example, as model size increases, what happens to the problem of privacy leakage? So using the Pythia model series, which keep the training data and schedule the same, while varying the size of models, we were able to study this problem and show that from the graph, you can see the red dots shows as the model size increases, the model performance increases, and the blue dot shows that as model size increases, the privacy leakage problem also worsens. The data extraction accuracy rate increases. And as we move to multi-model models, we also set out to explore this training data memorization issue, whether it appears in multi-model models as well. So from our work and also others' work, also showing that this issue also is prevalent in multi-model models, where by giving certain prompts that's similar to prompts used in the training data, these models, because they remember training data, they actually can generate outputs that are very similar to the original training data. And this is part of our work from our paper MMDT, Decoding the Trustworthiness and Safety of Multi-Model Foundation Models. This paper actually will be on the poster tomorrow at ICLR. And in this work, also, we provided a comprehensive evaluation framework for trustworthiness for many different perspectives, including privacy, for multi-model models. So when we started exploring this domain, when we started first to set out to investigate the question whether these language models can memorize training data and whether attackers can extract the data, that was just the very beginning, the initial investigation. By now, the field has grown a lot, and there have been many different investigations laying out a complex landscape of the memorization problem in large language models. And this is categorized in our recent paper overlooking this whole landscape. And I would say still, this is just the very beginning. There are many open questions and challenges in this domain. So first, what are the factors that actually impact memorization? How does, so our studies and others have studied model size, data deduplication, data cleaning, sampling methods. There's different factors that can influence memorization. But what are the other factors that can impact memorization? And how does training process impact memorization? And also, our work showed data extraction and other methods for detecting memorization. And others' work, especially some recent work, have shown that other methods, such as self-prompting, can even elicit or detect memorization even more effectively. So what methods and tools can we develop for more effective auditing and assessments of memorization? In fact, the examples that I illustrated, for example, the models can get into a weird state and start outputting training data. These type of issues indicate that models actually may memorize much more than what we currently can measure. So how can we elicit and measure such memorization more effectively? And also, our work and others' work have proposed various methods for mitigating memorization, including data cleaning, differential privacy, machine learning, activation steering, and so on. And however, these methods are still insufficient. What methods can we develop for more effective mitigation for memorization? In particular, also, what methods can we develop during the training process to mitigate memorization? So recently, David Silver and the recent Turing Award winner Rich Sutton released a paper called Welcome to the Era of Experience. The hope is that going forward, we can usher into a new era where we have these agents actually learn from real-world experiences and to be more capable and more intelligent. However, in this setting, I would say memorization and privacy leakage is even more important. It's even more important in this era of experience and agentic AI. As agents explore and learn from real-world experience through online and continuous learning, they will be learning from these real-world experiences that contain sensitive information. And hence, memorization and privacy leakage is even more important in this domain, and it's still yet to be explored. So that's the first example topic on privacy and memorization. So now I'll share some of the lessons learned from my journey on another very important topic as well, on robustness, in particular adversarial robustness. So 10 years ago at ICLR, the seminal paper on adversarial examples was published, showing that by just adding very small perturbations, sometimes even imperceivable to humans, perturbations, this, for example, to an image, this can cause image classifier to misclassify and still misclassify with a high confidence. My group was among the first to then investigate into this adversarial examples issue in many different deep learning systems and domains, and to devise new attack methods, including the first investigation for adversarial examples in generative models, deep reinforcement learning, and visual Q&A, and so on. And also we developed new attack methods beyond the traditional gradient-based optimization methods, for example, using GAN-based methods and spatial transformation methods to generate diverse new types of adversarial examples. And also developing new ensemble-based black box attacks to enable transferable targeted black box attacks. And also we're the first to explore the adversarial examples in the physical world and demonstrating that they can be effective and remain effective even under different viewing distances, angles, and other conditions. And we have the rare honor that some of the artifacts from our earlier work has now become part of the permanent collection at the Science Museum of London and help educate the general population about the importance of adversarial examples. So now, fast forward, with the rise of LLM, it's also important to investigate how effective and the consequence of these adversarial attacks on safely aligned LLMs. Again, in our recent work, Decoding Trust, we explored different perspectives on trustworthiness of large language models, and one of them is adversarial robustness. And by devising various different types of attack methods, and developing different adversarial prompts, our work showed that, again, these large language models can be easily attacked with these, even just very simple adversarial prompts. They can cause the LM to give the wrong answer and misbehave. And in fact, our work analyzed across all leading large language models, and our results show that today's LLMs can be easily attacked and have many different types of risks for trustworthiness. And again, for the work that will be shown tomorrow at this conference, we also extended the work, the adversarial robustness for multi-model models, and again, illustrating that these multi-model models actually, they're even easier to attack. You can give adversarial prompts that will cause the models to generate the wrong image, or you can give adversarial images, then can cause the model to actually give the wrong answer to image queries. And I welcome you to go see our poster tomorrow. Adversarial attacks are not only effective at inference time, as I have shown, called adversarial examples, they can also be effective at the training stage, including pre-training and fine-tuning, and this is called data poisoning. So my group, again, was the first to investigate data poisoning and targeted backdoor issues. So early on, our work shows that back then, for a facial recognition system, we can, through a very small fraction of very stealthy poisoned data injection into the training data, we show that the attack can cause the model to learn the wrong model, such that during normal circumstances, the model actually behaves fine, recognizes the faces correctly. But however, when any user in our tests wear a particular type of glasses, so this is a physical attack, wear a particular type of glasses, it will cause the facial recognition system to misrecognize the person into a particular target person. So fast forward, in the age of large language models, this data poisoning attack can cause even more severe consequences. Recent work from Anthropic also showed that with this data poisoning and backdoor attack, it can cause the model to, again, learn the wrong model, such that during normal circumstances, the model will generate fine code. But however, when certain phrases appear in the prompt, the model will start generating vulnerable code. And this issue can still persist after the model has been safety tuned. And our recent work in Europe also illustrated further that this type of data poisoning attack actually can be even effective without training. It can actually happen during the RAG stage in our agent poison work, showing that this data poisoning can cause the agents to essentially retrieve malicious trajectories in the RAG database when certain trigger phrases appear in the prompts. So these are a few examples illustrating a general trend that we have seen from our work. So as I mentioned earlier, on one hand, we are really enjoying the great progress of AI advancements. However, what we have seen also as our work and others' work have shown that as model and AI advances, unfortunately, the level of risks grows significantly or drastically. However, unfortunately, our level of understanding and also our defense and mitigation capabilities grow much slower. And the gap between the risk level and our understanding of these AI safety issues widen as AI advances. And also the gap between risks and defense capabilities also widen as AI advances. So on the left here, I'm just illustrating one example. So when we started working in AI safety, that was the early days, pointed by the red arrow. Back then, each year, there were only very few number of papers, maybe a handful of papers. The field since then has grown exponentially. Now, every year, there are thousands of papers in this domain. However, unfortunately, most of these papers are actually in the space of attacks, on the attack side. So the community has been really productive and creative in devising various new attack methods and so on. But however, in contrast to rapid progress in new attack methods, progress in adversarial defenses has been extremely slow. And today, we have no effective general adversarial defenses. As I mentioned, current AI alignment mechanisms are easily evaded by adversarial attacks. And any effective AI safety mechanisms need to be resilient against adversarial attacks. And hence, adversarial robustness is a huge open challenge for achieving AI safety. In order to address all these challenges, we need to develop solutions throughout the different stages of AI lifecycle. So first, we need to develop better techniques and tools for AI model understanding and evaluation, as I showed earlier, including black box evaluation frameworks and benchmarks, as well as white box interpretability methods. And also, we need to develop various techniques for AI model hardening and alignment throughout the different model development stages, including data preparation, post-training, and so on. And also, we need to develop effective solutions for AI model monitoring and control during model inference and deployment. And also, we need to develop and also there's a need to develop new paradigm and frontier for safe and secure AI to provide even greater solutions and guarantees. So again, as I mentioned, the current solutions are insufficient, and today we still don't have general effective adversarial defenses. So here I want to just briefly mention some of our recent work with our collaborators as some initial steps to further explore this important domain. So one recent approach with our collaborators is on representation engineering. In contrast to approaches such as mechanistic interpretability, representation engineering is a top-down approach to interpretability. And what we do here is we actually build models that's by observing the model activations during inference time to try to learn to try to categorize the behaviors of the model. So there are various different techniques and approaches to achieve this. So in this particular case, we provide we use contrastive stimulus and task to use that to feed to the model and observe the model behavior under these contrastive stimulus and tasks. And using this approach, we can then learn actually fairly simple models, such as linear models, and identifying our work was able to identify, for example, certain directions in the activation space at different layers that correlates with different types of model behaviors, such as whether the model is hallucinating, whether the model is honest, and so on. And we call this representation reading. And even more importantly, with one step further, in addition to just being able to try to identify models' behavior using the model activation, by using the learned model, we can actually do what we call representation control. So, for example, by amplifying the model application, model activation along certain directions that we have identified, this can help, can modify model behaviors. For example, making the model more honest or more dishonest. I do view this as a really important direction, given that this is a unique advantage we have for these artificial neural networks versus the brain, is that we have full transparency and control of these neural networks, that we can see their activation during inference time, and we can modify activation during inference time. So this is an important arsenal in our toolbox for AI safety. So in our recent work, we studied political leaning of large language models and showing that today's large language models, they have left leaning. And using representation control methods, we were able to show that we can use representation control methods to mitigate such issues. And we can identify certain directions in the model activation space that helps align to make the model, for example, more neutral and so on. And then by using representation control, modifying these activations during inference time, as you can see from examples here, the model response under representation control, now instead of being left-leaning, it actually can be now much more neutral. So just diverge a little bit. So this work, using this representation control, we can show that we could make the model response more neutral. But however, what is the right way to really handle the, for example, political leaning of these large language models, and what are the potential influences of large language models on our democracy? It's a much more complex topic. This can have huge implications for our future democracy. So we also have a blog at ICLR, at this ICLR, going into more detail to explore this important space. And you can also you can see also more information at this website as well. So the methods I mentioned, such as representation engineering, is one step forward, but however, it doesn't really help us to provide any quantitative guarantees. So recently, with a number of leading researchers, we launched a new initiative called the Quantitative AI Safety, aiming to develop new paradigms and new approaches to provide a quantitative foundation for AI safety, which I will talk a little more in the later part of my talk. So that's the first part. Some lessons learned from my journey on ensuring trustworthiness of AI and AI alignment. So now I will move to the second part of my talk on how to mitigate misuse of AI. So earlier, I mentioned that as we enjoy the AI advancement, at the same time, we need to consider a broad spectrum of different types of AI risks. However, I do personally believe that cybersecurity will be one of the biggest AI risk domains for a number of reasons. Attackers have diverse incentives to launch attacks, and today attacks already cause huge damages, and increased AI capabilities, such as the recent advancements on coding and reasoning, they can significantly reduce attack costs and increase attack scale. And also today, we already see Gen AI causing orders of magnitude increase in attacks, in particular for attacks on humans, such as phishing and social engineering attacks. So the key question is, how will frontier AI change the landscape of cybersecurity? So in traditional cybersecurity, we have attackers and defenders, and we have traditional software systems which have symbolic programs written by humans. Now with frontier AI, both attackers and defenders will be armed with frontier AI. And also the software system becomes more complex in what I call hybrid software system, which includes both symbolic programs written by humans and AI, and also non-symbolic components, such as AI models and neural networks. Given that AI is dual-use technology, it can help both attackers and defenders. So the key question is, who will AI help more, attacker side or the defender side? In our recent work, we are among the first to set out to investigate this important question. In particular, we utilize a marginal risk assessment framework to help analyze the marginal risk of frontier AI in the landscape of cybersecurity. In order to do this, we need to know the enemy, analyze the impact of misused AI in attacks, and know the defense, analyze the impact of AI on defenses, and we need to analyze the natural asymmetry between defense and offense. And I will also share some of the lessons and predictions from our work. So first, looking at the impact of misused AI in attacks. Misused AI can help make attacks more effective. And there are two broad attack domains that we need to consider. One is how attacks can attack machines, computer systems. And the other one is how attacks can attack humans, such as phishing and social engineering attacks. Cybersecurity attacks are very complex. A successful end-to-end attack often contains many stages together called a kill chain. To do this analysis, we need to analyze the impact of a frontier AI in each stage of the attack kill chain. So my group, almost a decade ago, we were the first to investigate using deep learning for program binary analysis and vulnerability detection. Even back then, using graph neural networks, we were able to show that deep learning-based approaches can achieve state-of-the-art in binary code similarity detection. And using this approach, we were able to actually detect vulnerabilities in program binaries in the real world. And fast forward, with the advancement of LLM, for example, Google recently has shown the first public example of AI agents finding zero-day vulnerabilities in widely used real-world software in SQLite. However, the recent benchmarking, for example, Cybench, which analyze agents' capabilities on professional CTF tasks. So these are more, instead of just finding vulnerabilities, these are more end-to-end tasks. However, still simpler, like CTF tasks. So Cybench has shown that for today's best models and with the agents that they have tried, the most complex, difficult problem that the agent can solve has the first solve time, meaning the fastest human solving time, so only 11 minutes. And with other more complex tasks, these agents fail. So this illustrates that the current models and agents are still, it still has limited capabilities for these end-to-end attacks. And So these are a few data points. So in our recent work, we did the first comprehensive study in this domain, surveying several hundred papers published recently overall in this domain, and looking at the AI capability and impact levels in different attack stages. And our work illustrated that currently the AI capability and impact levels in these different attack stages are still fairly limited. And with most of these stages only has very limited demonstrated effect in the real world. So this is the attack on machine side. On the other side, we have a very different story for attacks on humans. So first, humans are the weakest link in computer security systems. Statistics has shown that actually most of the penetration attacks actually start with a social engineering attack. And today, the most common cyber threat facing businesses and individuals is phishing. And also, as I mentioned, GenAI today has already caused orders of magnitude increase in social engineering attacks. So, and hence, for frontier AI in attack side, it's the uplift is uneven. For the attacks on humans, attackers are leveraging GenAI already very effectively, whereas whereas AI capabilities and impact level for other stages of attacks today is still limited. And when we investigated AI capability and impact levels in defense side, unfortunately, our study shows that the AI capability and impact level is even more limited, with most of the stages for defenses have extremely limited impact from frontier AI. In some stages, there's even no demonstrated effect, and in some stages, there's only demonstrated effect in research papers. So our goal is to further improve AI capabilities for defense. However, given the dual-use nature of AI technologies in defense and offense, this creates a particular challenge for using AI to help in cybersecurity. So our study showed what we call equivalence classes. So there are these equivalence classes of the defense capability, the same AI technology that can be used to improve a particular defense capabilities. There is a corresponding attack capability that the same technology will help improve. And our paper gives a list of such examples of equivalence classes at every stage of attack and defense stages. To make things worse, there's natural asymmetry between defense and offense. So when I talk to people about this issue, oftentimes an answer here is, actually, we don't need to worry. Defenders can use AI to discover and fix bugs before attackers, and hence there's no need to worry. Is this true or false? What do people think? True or false? Okay, good. So the answer is false for a number of reasons. So one, offense side only needs to find one attack that works, whereas defenders need to fix all bugs and prevent all attacks to succeed. And also cost for defense oftentimes can be much higher than attacks. And also deploying defense, even when it works, can take a very long time. One needs to develop, for example, patches to fix the bugs, and then need to do a lot of testing to make sure the patches doesn't cause other problems, and then need to roll out the patch globally. However, a lot of legacy systems, even when patches exist, are still not patched. For example, the current mean time for certain statistics, current mean time to deploy remediation in hospitals is close to 500 days. And also, attackers can even learn about vulnerability and generate exploits using public information on patches without even having to find 0 days, and can use this information to exploit systems before they can be patched. And our earlier work also has demonstrated this as well. And in fact, there are many such asymmetries between attacks and defense that actually favors the attack side. For example, there's also asymmetry between cause of failures between attacks and defense. Attackers have high tolerance for failures. They can try out many attacks. Many of them can fail. As long as some succeeds, attackers still win. Whereas defenders have very low tolerance for failure. If they fail, that means attackers have succeeded. And also there are different priorities for adopting AI technologies, different priorities of scalability and reliability. Attackers prioritize scalability. They want to launch large-scale attacks on huge number of targets. As long as some succeeds, the attacker will still win. Whereas for defenders need to prioritize reliability, since defenders need the system to work reliably even during normal operations as well. And also, as I mentioned, with frontier AI, the subject systems become even more complex as hybrid systems that contains both traditional symbolic program components as well as non-symbolic components, such as these machine learning models. And these frontier AI introduce new marginal risks to hybrid systems at both model and system level. And unfortunately, today, we have very little existing defense for hybrid systems. So the consequence of misused AI in attacks is vast. As I mentioned, today we're already seeing misused AI in attacking humans. And in the future, misused frontier AI can completely change the attack landscape, can help with every attack stage, apply to every attack domain in the attack landscape, can increase attacker capability, devise new attack methods and strategies, reduce resources and costs needed for attacks, and completely change the economic landscape of attacks, and can automate large-scale attacks and make attacks more evasive and stealthier. So the question is, what can we do to address these issues? What can we do to actually help defenders more? So in my own work for the past several decades, as well as the overall security community, there has been several paradigm shifts for security defense solutions. So the first one is reactive defense, where defenders try to detect attacks once the attack happens, such as detecting malware and block malware. We call this reactive defense. So AI can help enhance reactive defenses, for example, by improving attack detection and analysis. However, there are many challenges. Attackers can also use AI to make attacks more evasive, and attack detection needs to have low false positive and low false negative rates. And attacks may happen too fast with AI for effective response. And hence, for reactive defense, AI may help attackers more than defenders. So the second paradigm for defense is proactive defense by bug finding. However, as I mentioned earlier, in this case, still, AI can help attackers more than defenders, at least in the near term. So the hope and also my proposal is to use AI to help us build proactive defense, the third paradigm, which is proactive defense through secure and safe by design and by construction. In this approach, we architect and build provably secure programs and systems in contrast to bug finding and attack detection and reactive defenses. We can formally specify desired security properties and safety goals and so on. And using formal verification, we can formally verify whether a program satisfies the desired security properties and safety goals. In fact, I would say that we have entered the era of formally verified systems largely thanks to the efforts from the formal verification community. We have many formally verified systems, including microkernels, file systems, compilers, and so on. However, these systems have not been widely deployed, mainly due to the fact that it's very labor-intensive to do the proofs. For example, ICLR took tens of proof engineers to prove. And when you change the code, you need to change the proof also. In order to address this issue, my group was among the first to use deep learning to help automate theorem proving. So quite a few years back, together with other researchers, including Ilya from OpenAI back then, we demonstrated that by using deep learning, we can help automate certain steps in theorem proving. However, back then, technology was still early, and we have limited compute. So today, I strongly believe that we have reached an inflection point, leveraging the advancements in in frontier AI. We hope that we can develop stronger capabilities to automate theorem proving. So in our recent paper with other collaborators, we set out to lay out the roadmap to advance the frontier AI for formal mathematical reasoning. Using this approach, instead of having built AI agents to just play games like Go, we hope to have AI agents to help automate theorem proving for program verification. And when used together with program synthesis, we can not only generate code, we can actually generate proofly secure code, where we can generate code with the proofs that the code actually satisfies the desired security properties. Using this approach, we can reduce the arms race and utilizing AI to build properly secure systems. And using this way, AI can help defenders more than attackers. In order to truly accomplish this, we need to significantly enhance the capabilities of frontier AI for formal mathematical reasoning and theorem proving. And again, in our recent paper, we lay out the roadmap to advance the domain for using AI in formal mathematical reasoning and theorem proving. Given interest of time, I won't be able to go into the details. By utilizing, in the paper, we lay out the roadmap to address the current open challenges and future directions in AI for theorem proving, including how to overcome scarcity of formal data, as well as developing more advanced algorithms for proof search. By using AI technologies, we can develop various approaches for addressing the scarcity of data issues, including using AI for auto-formalization to auto-formalize informal math into formal theorem statements and proofs, and also generate synthetic data from, for example, mathematical axioms and through neural conjecturing. And also, we need to explore various algorithms, how to scale auto-formalization, for example, leveraging feedback from theorem provers, and also utilizing test-time compute to scale up proof search, develop effective value models for us to assess and prioritize proof goals, and exploit hierarchies in theorem proving. So in our paper, we lay out also a roadmap with the hope to bring the community together to develop milestones and guideposts, systematic benchmarks, datasets, algorithms, and various tooling to enable collaborative open source efforts to together advance AI for formal math and theorem proving. And you can check out our paper here. And with the current advancements of AI technologies, we are seeing code generation. There's estimates that there's already 50% of code is generated with AI, and going forward, there will be even more. So one question is, how safe and secure is AI-generated code? For example, in our recent work, we showed that even the best model, they have severe limitations, and they can limitations in generating secure code. Oftentimes, they can generate vulnerable code. And hence, instead of just doing code generation, we need to do verifiable code generation. So in our recent work, we started the first investigation and built the first benchmark for end-to-end verifiable code generation. And from our evaluation, the current models and agents are still insufficient. But however, we hope that by further advancing this domain, we can really enable AI agents to enable the generation of provably secure code. And this is also the first step for our quantitative AI safety initiative as an example of a first step. So, so far I've talked about how we can use AI to help build provably secure systems to achieve secure and safe by design. However, so far I only talked about traditional systems. But however, as I mentioned with Frontier AI, we are going to have hybrid systems. And these hybrid systems can pose additional challenges for a formal verification-based approach. For example, for non-symbolic components, such as neural networks, we sometimes don't even have precisely specified properties and goals. And hence, going forward, we also need to extend this approach to hybrid systems. For example, LLM agents and agentic systems, these are hybrid systems, and they have increased attack surface, and many things could go wrong in these agentic hybrid systems. In our recent work, we also developed a new framework for secure agents to enable programmable privilege control and guardrails for LLM agents. And we hope that we can further extend such work to enable provable guarantees even for the agentic AI setting as well. So far I've talked about defenses for AI, for attacks against computer systems. And also we need to develop defenses for humans against attacks. And here I do also believe that the AI can provide the only defense against social engineering and phishing attacks. So with that, I wanted to just summarize some of the lessons learned. AI will help attacks more at the beginning. Current systems are highly vulnerable and ill-prepared for AI-assisted attacks. And as cost of attacks going down, we expect to see unprecedented increase in attacks. The world was not prepared for pandemics, such as COVID, despite early warning, and attacks assisted with AI can be much worse. So I'll also share some lessons learned from the medical device security. So my group with collaborators conducted the first medical device security analysis in the public literature. And we showed that we identified critical security vulnerabilities in medical devices such as defibrillators. And back then, the FDA medical device approval process didn't even mention security. Only a few years later, following our work and others' work, FDA changed their approval process and issued guidance recommendation on medical device security. So overall, security space is complex. Frontier AI will have a huge impact in cybersecurity. And hence, it's important to learn from past lessons and act now. So far, I've talked about the two parts from my own lessons from my own journey, ensuring trustworthiness of AI and AI alignment, and mitigating misuse of AI. And my own journey essentially progressed through these several different stages. First, to uncover new critical issues and explore limitations for better understanding. And then through systematic evaluation for better assessments by developing systematic evaluation frameworks and benchmarks. And then develop new approaches, paradigms for better protection and assurance. So the overall goal is to advance safe and secure AI innovation to ensure its potential benefits are responsibly realized and widely shared. And to achieve this, technical solution alone is insufficient, and we need a socio-technical solution. So to enable this, recently we launched a proposal for a path for science and evidence-based AI policy, together with many leading AI researchers. And the key point is that we believe that AI policy should be informed by scientific understanding of AI risks and how to successfully mitigate them. And we need to prioritize advancing scientific understanding of AI risks and how to successfully identify and mitigate them. So the proposal lists out 5 different priorities and a call to action, and has gotten wide support across industry, academia, and civil society. And we have volunteer contributors from close to 300 institutions volunteer to contribute. And also this has served as a base for reports, for recent reports to the California Governor Newsom. And we have many next step plans to work with the community together to push forward to advance scientific understanding and the science and evidence-based AI policy. So I think I'm running over. I will just finally quickly summarize. So why it's important to work in AI safety? So first, for society, we hope to advance safe and secure AI innovation to ensure its potential benefits are responsibly realized and widely shared. And even if you don't care about this, if you are just companies and practitioners building and deploying AI solutions, you need to protect your AI systems from malfunctions and attacks and ensure your AI system does not do harm to others. And even if you don't care about this and you are just doing research, still, the area of AI safety and security is extremely intellectually stimulating, requires a lot of creativity and out-of-the-box thinking, and less reliance on huge resources, and offers some of the hardest problems to solve. And also, as I mentioned, we are seeing widening gap in the space, and the space is severely under-investigated. So with that, I want to thank everyone. And if you're interested in reading our paper on AI risk in cybersecurity and help with our recent survey, you can scan this form. And also, if you're interested in learning more about agents, you can sign up to our MOOC, Massive Open Online Course, with over 23,000 enrolled. And also, we have an Agent X competition that's currently ongoing, and you can join here. And finally, I just wanted to briefly mention that please also check out our presentation and poster tomorrow on data sharply in one training round. Thank you.
Yeah, I think very nice talk. Thank you for the detailed explanation of the new threat models coming into the hybrid system. So traditionally, we solve the different threat like integrity and privacy through like protecting the data and also the control flow, right? So now when the token flow came into play, how would we like formalize and prove that? Any thought?
Sorry, could you repeat the last part?
When the token flows into the hybrid system, right, with neural network and other things, how we solve that?
I see. Yes, as I mentioned, so these currently are open challenges, but we do hope that by essentially placing, so in this case, you do need to place various guardrails and sandbox around these non-symbolic components, and that can provide essentially certain type of guarantee, and then overall you can enable potentially you can enable certain guarantees for the overall system.
Okay, yeah, hopefully.
Right, so these are still big open challenges. Yes, thank you.
Hi, thank you for your insightful talk. I have a question about the machine learning bit. I'm wondering what the main advantages and limitations you will say when it comes to debiasing machine learning models in fairly sensitive domains, and how good machine learning is to deal with entangled input features, where the protected features might have hidden correlations with non-sensitive, non-protected attributes.
Okay, great. Yeah, thanks for the question. Yes, I think machine learning is a very exciting domain and very interesting direction to explore. But currently, yes, there are many limitations. Oftentimes, so one is actually difficult to evaluate. Even when there has been work showing, okay, maybe something has been unlearned, but actually later on you can show that there are other ways where actually it has certain, for example, knowledge has not really been unlearned. You can still actually extract the knowledge in other ways and so on. So how we can actually do effective unlearning and also really be able to evaluate the effectiveness properly is still a big open challenge. But it's a very interesting direction to further explore.
Hi, Dawn. Thank you for the excellent talk. Excuse me. I wanted to ask about the part at the end on the formal approaches to AI and AI safety. How do you avoid the problem that Psych encountered that formally representing common sense knowledge is basically impossible? So the system might be some neural blob, right? And we know the power of embeddings and data-driven approaches. But if you want to prove something, it has to be symbolic. And we don't know how to write down the desirable properties for many of these systems, right? Like fairness, like the question before asked, or political bias. Like, how do you formalize something like that?
Right. Yeah, this is a very good question. Right, exactly as I mentioned, I think for traditional software systems, I think we can actually use AI to really make significant advancements to automate theorem proving and be able to significantly improve our capabilities for formally verifying those traditional systems.
No, I don't mean the proof. I mean the
right. So as I mentioned,
desirable property.
Yes. So that's actually part of the bullet in my slide as well, is that for these hybrid systems, as I mentioned, it actually has challenges. For certain properties, you actually don't even have formally specified properties. So for example, if you want autonomous vehicle not to drive over a pedestrian, you don't even have formal specification of a pedestrian. And also, as examples you mentioned, other types of properties and so on. So yes, these are big open questions, how we can further extend this type of approaches to, these hybrid systems. These are, yes, big open questions. So that's what I mentioned as well. Yeah. So I think these are important questions for the community to further explore.